Welcome everyone to this session on hypothesis testing in R by Dr. J.K. Sachdeva. In this lecture, we will learn how to perform statistical hypothesis tests such as the one-sample t-test, two-sample t-test, paired t-test, and one-way ANOVA with post-hoc tests. Each concept will be explained step by step. We will see the data, the R commands, and how to interpret the output.
Hypothesis testing allows us to make inferences about a population using a small sample of data. We begin with two statements, the null hypothesis, which assumes there is no difference or no effect, and the alternative hypothesis, which assumes there is a meaningful difference or effect. Using data and probability, we decide whether to reject the null hypothesis.
How are hypotheses written in each case? One sample t-test. Null hypothesis mu is equal to hypothesized mean. Alternate hypothesis mu is not equal to hypothesized mean. Two independent sample t-test. Null hypothesis, both groups are same, or you can write A is equal to B. Alternate hypothesis, both groups are not the same. Paired t-test. Null hypothesis, after is equal to before. Alternate hypothesis, after is not equal to before. ANOVA. Null hypothesis, all groups are same. Alternate hypothesis, any one of them is different.
Before performing any test, we need to prepare our data. All datasets are saved on the desktop for easy access. In R, we use the command sample_data read.csv, c /users /Sachdeva /desktop sample_data.csv. Then we can view and understand the structure of the data using head, data, and str, data. Let's now begin with our first test.
The one-sample t-test checks if the mean of our sample differs from a known or hypothesized population mean. For example, we test whether the average score in our sample differs from 70. In R, the command is t.test sample_data $score mu is equal to 70. Please note how we put $ between the data file and the concerned variable. If the p-value is less than 0.05, we reject the null hypothesis and conclude that the sample mean is significantly different from 70. Otherwise, we accept that the mean is statistically similar to 70.
Let me show you the data first, which I am going to use for the analysis. The first data is sample data.csv, which we are going to read in our program. Then data is group data, which is the marks or scores for male and female, and we are going to analyze whether there is a difference between male and female. Third data is a paired data, which we have given the as before and after. It's an experimental data. We have given the treatment and what was the score of the individuals before and after, which we are going to use for ANOVA data. It has been named as ANOVA data.csv, and the file has been created as a group and score. These are the two variables. Groups are A, B, and C, and score is given here. And this way we are going to do the ANOVA analysis. Further, I have created all the commands which I am going to use for analysis one by one. Let us first set the directory, because all my folders, all my files are in the folder R databases. So I am going to first set the working directory as R databases. You can save it on desktop, you can save it on this, but note it is a backslashes, and then we get the working directory. I am going to run this part only. Okay, now it first says the set working directory, it has been set, and then working directory is C user Sachdeva desktop or databases. You can have your own. Now all the working, all the outputs, we can put it in this database. Now let us run our first test, that is ttest. The file which has got the sample data, their data is given. I can show you. For let us run this, and now the sample data file is given there. So these scores are given. First 5 scores have given had sample data. Now I will run by hypothesized mean is 70. So let us run it now. Now T stat is 2.5002. Degree of freedom is 14. P value is 0.0254. So now this is less than 0.05. So we can have the alternate, that is true mean is not equal to 70. So our null hypothesis was true mean is equal to 70. Alternate hypothesis, true mean is not equal to 70. As the p-value, this p-value is less than 0.05.
The two-sample t-test compares the means of two independent groups, such as males versus females or control versus experimental groups. The R code is group_data $group as .factor, group_data $group. Head, group_data. T.test, score tilde group, data is equal to group_data, var equal is equal to true. If the p-value is less than 0.05, we can say that the two groups have significantly different means. If not, their means are statistically the same.
Let us run the two independent sample t-tests. So let me first group data, that we'll have in the variable group data, and group data will be done as factors group data, which is the group data that is on the group. So let us first run it this. So then we can see the first 5 entries group score. Now let us run the t-stat for two independent data. Okay, so we are going to run it. In this case, the t-stat is p-value is 0.007291. It is less than 0.05. So we can say the alternate hypothesis, meaning true difference in means between group female and group male is not equal to 0. So mean are given 76, mean in group male is given as 71. Right?
A paired t-test is used when the same subjects are measured twice, for example, before and after an intervention. The R code is paired_data, read.csv, paired_data.csv, head, paired_data, t.test, paired_data $before, paired_data $after, paired is equal to true. If the p-value is less than 0.05, it means there's a significant change between the two related measurements. Otherwise, the difference is not statistically significant.
Let us run now paired t-test. Paired t-test data, that is before and after, I'm going to run it. Now in this case also, the p-value is less than 0.05. What does it mean? 1.801 E raised to 0.07. That is E07. What does it mean? It means you have to put 6 zeros before 1. That is 0.000001. So it means this is less than 0.05. So we have got the alternate hypothesis, meaning true difference mean is not equal to 0. It means there is a difference between before and after.
Before running any t-test or ANOVA, we must check that our data is approximately normal. The command used is Shapiro.test data $variable. If the p-value is greater than 0.05, we can assume that the data is normally distributed and we may proceed with parametric tests. If not, we might need to use non-parametric alternatives.
We can test the normality by Shapiro.test ANOVA data $score. That is the variable which is score. We are going to check the normality test by Shapiro test. We will run it and we see the p-value is 0.8794. So our data is normally distributed.
When we have more than two groups, we use a one-way ANOVA to test if at least one group mean differs from the others. In R, we use the following code: data read.csv c /users /Sachdeva /desktop /ANOVA_data.csv. Model AOV score tilde group data is equal to data. Summary model. If the p-value is less than 0.05, at least one group mean is significantly different from the rest.
ANOVA. Let me first clear it everything because this will be clear to you. Run. Now in this case, first of all, it has shown me the groups, group A, B and score, and then it has shown me the ANOVA table. In the ANOVA table, the p-value is 0.0039. It means this 0.000 means one, it is less than 0.05, or you can even say less than 0.001. So it is statistically significant. There is a difference. What does it mean? There is an alternate hypothesis, meaning any one of them is different. ANOVA always has the hypothesis, all are same, any one of them is different.
Once ANOVA shows a significant difference, we use a post hoc test to find out which specific groups differ. The most common method is Tukey's HSD test. In R, use Tukey HSD model. The output lists all pairwise comparisons, showing which groups differ significantly and by how much.
When any one of them is different, we'll have to do post hoc test. Which one is better, which one is not better. So let us now run it. Tukey HSD with ANOVA table. So I'm going to run it. So now we have got the difference between B and A is 4. B and A is 4 and the P value is 0.029. It means there is a significant difference between B and A. Then C and A, 8.5. That is also a significant difference, 0.00318. CB, 4.5, and the significance difference is 0.021. So now highest difference is between A and C, and the next one difference is between C and B, and the next difference is between B and A. So now you can arrange it. The highest one, highest.
When reporting statistical results, always include the name of the test statistic, degrees of freedom, and the p-value. For example, T28 equals 2.45, P equals 0.02,
indicating a statistically significant result. Clear reporting ensures transparency and reproducibility in research.
To summarize, we learned how to conduct the one-sample, two-sample, and paired t-tests as well as one-way ANOVA with post-hoc tests using R. You can apply these methods to your own research data by replacing the file names and variables. Thank you for learning with us, and happy coding in R. Next video on correlation and regression with R. Always like if you learned.